This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
So building flow domains with ANSYS DesignModeler. What we're going to talk about today, some basics of flow domains, why we need them and how to extract them. Why use ANSYS DesignModeler? Most of you are probably using a CAD tool, so why do we want to use or learn and use ANSYS DesignModeler to do this? And then we'll go over some extraction techniques for flow domains as well as some geometry simplification tools. And I'll be doing some live demos along the way. This way we can see what we're, how to use each type of operation. Okay, so one of the first steps in any CFD analysis, after we've decided that CFD is what we want to do, we have some goal in mind. Let's say we want to predict the pressure drop, or maybe we want to find the lift or drag over an object. Once we identify that CFD can provide us those qualities, we need to determine the extent of the flow domain over which we're going to solve the governing equation. So how big of a domain, whether it's internal or external, do we need to include in order to get the information that we're looking for? Now, oftentimes, this requires isolating a section of a larger physical system. So for instance, if we had a single valve and an entire piping network, it's generally impractical to solve the entire piping network if we're really only interested in just one tiny section. So we're going to try to isolate that component that we're interested in and solve the governing equations just in that section. So when we do this, that means that we have to cut out this part of an overall larger system. And we want to make sure that we do that wisely. The extents of the domain are going to be where we're placing our boundary conditions. So we want to make sure we have information at the places where we cut the boundaries. So we want to try to choose the extents of our domain based on the information that we know we have. So do we have a flow rate somewhere? Do we have a pressure? Maybe we have a velocity profile. Try to use that information to guide how you determine how large your computational domain is going to be. So once we've identified the overall shape and extents of the domain, we have to go ahead and then extract it. Now, before we do that, or before we discuss how we go about doing that, an important note is to understand that we can generally divide flow domains into two basic categories. We have internal flow domains, so flow through pipes or pumps or anything else where the flow is bounded on all sides by walls. On the other hand, we also have external flow domains where we have flow around an object, like a building or an aircraft or the hull of a ship, where it's not necessarily bounded on all sides by walls, but maybe it's over an object or something. Now, we can, of course, have a combination of the two, but it's important to make this distinction so that we know which tools within ANSYS DesignModeler we're going to use in order to extract our flow domain. Which brings us to our next point. Why are we going to use ANSYS DesignModeler? Typically, when we have a CFD analysis in mind, we're going to start with an existing CAD part. Maybe you made it in your CAD program or someone in your organization did. And you probably think, why, if I already have this CAD tool and I already have the CAD part, why would I want to go ahead and use ANSYS DesignModeler? Well, there's a couple of different reasons. First, ANSYS DesignModeler has CAD import tools which allow us to combine parts from different CAD programs. So ANSYS is what we call CAD neutral. They show no preference to any one CAD vendor. So if you are working on a part, maybe you have a CAD part from a supplier, and maybe you have a CAD part from your own organization, and maybe they come from different CAD programs, you can easily combine those in ANSYS DesignModeler into one database. In addition, ANSYS DesignModeler allows us to make changes to that geometry without affecting the original CAD file. So we can do things like geometry simplification, where maybe we want to get rid of some detail that's not really necessary for our analysis, and we can change the CAD, the geometry inside of ANSYS DesignModeler without affecting the CAD file that's required maybe for production purposes. And finally, we have streamlined and simple flow domain creation tools. So this process, or ANSYS DesignModeler, is uniquely designed for preparing your geometry for analysis. So we've created tools inside of ANSYS DesignModeler that make extracting flow domains a very simple and straightforward process. And we'll see that as we go on. Okay, so our first topic is geometry simplification. One of the most important tools, or the most used operations that I take advantage of in my day-to-day analysis work is the face delete. From the tools menu, we can insert a face delete, and we use this to simplify our existing parts and removing unnecessary features. So we can see in the picture below we have an electronics board, and maybe we're solving for the airflow over it, a conjugate heat transfer analysis. And as part of that, we have screws connecting the multiple boards. Now, if we're solving the airflow, it's pretty unlikely that the detail on the head of the screw is really going to affect the flow in such a manner that we need to resolve it. And in addition, resolving those details are going to be very cumbersome in any measure. Right? We're going to have a large number of cells inside of those details, and that's going to be really unnecessary in the grand scheme of things. So by using the face delete, what you see is we can get rid of that topology. So ANSYS DesignModeler will use the surrounding topology and try to delete the feature by paving over it. Now, what's nice about this is it's not subject to the parent-child feature relationships from CAD. These are not necessarily being translated back to your CAD file. So this is just for analysis pre-processing. So a very useful tool, and I'll show you an example of something like that. It's going to become a key to doing successful CFD analysis. Another tool that we use is the merge operation. Now the merge operation is available for CAD files when we have more detail than is really necessary for analysis. So for instance, if we look at the pictures on the bottom of the slide, we have an edge highlighted that is split into 6 sections. Now, for meshing purposes, if it's split up in that many sections, we're going to have to resolve with a few elements each one of those sections. So that makes meshing more cumbersome. Using the merge operation, we can simplify that into just one edge. And a similar thing goes for the faces of the fuselage we see in the lower picture. So we can simplify the topology definition, but not lose any of the detail. Additionally, one of the nice parts about the merge operation is that we can use an automated search feature. So we can automatically have DesignModeler go out and search for or faces or edges that it deems appropriate for merging. And then you can review and have it go ahead and generate. Another tool that we have is the Repair Tool menu. The Repair Tool menu gives you options to fix small edges, small faces, spikes in your model, really do some very general automated cleanup. And this is a very, very powerful set of tools here. It will go out and search your geometry and try to identify areas in which later on you're going to have difficulty meshing. So I certainly suggest that everybody go ahead and try to use these as much as possible. They will help alleviate many a meshing headache. I know it's certainly helped me in the past very much. And you can see where we've gone from the fuselage up top to a very complicated definition to a much simpler definition on the bottom. So again, automated search tools that can help us simplify our geometry. Okay, at this point, what I want to do is we're going to take our first break, and we are going to do a poll. So let me get that set up here and open it up. Again, we want to have you participate in these for the PE credits. So So let me open that one up here, and we'll take about a minute and hopefully get everybody's responses on how much time you guys are spending cleaning up geometry. And it looks like, just reviewing the results here, that we have most people spending, a fair amount of time doing CAD cleanup. I mean, that's pretty typical of analysis. That's typically how things go. You have a geometry that you're given, and you need to prepare that for analysis. So these tools become very important. Okay, let's go back to our PowerPoint here. And so once we do our geometry simplification, again, I think it's always easier to do that before we go ahead and extract our flow domain, because I think it's easier to operate on the solid CAD geometry rather than the flow domain itself. So I try to do that before I do any extraction. So once we've done that sufficiently, and it's usually not going to be a one-time process. We may have to go back and forth, but after we've done it to where we think we're good enough to extract the flow domain, we can go ahead and do that using one of two different tools. Now, the first we're going to use for internal flow domains, and that's the fill operation. What the fill operation does is create a frozen body from the internal void in your CAD part. And we have two ways of defining this, so a little bit of flexibility. The first is what we call bicavity, and this requires picking all of the faces that define the internal void. So if we look at the picture below, we have a manifold here where there's maybe 40 faces on the inside, and we pick all of those, and once we generate the operation, on the right you can see the resulting flow domain that captures those internal voids. Now, conversely, if the internal structure is too complicated to pick all the faces, what we can do instead is use the bicaps method. And what this requires is that we create surface bodies that will cap the openings of the void. And I'll show you that in our demo, which we're going to get to right now. So let me drag in Workbench a geometry component into the project page and open that up. And I'll go ahead and import an external geometry file. So the first one we're going to do is a ball valve assembly. So I'll generate that. And you can see what we have here is a ball valve section, and alongside that we have some piping that's attached. So we want to go ahead and extract this internal flow domain. So let me hide this pipe here, and we can see we have some complicated structure on the inside of the ball valve section. But if we look at the piping section, we have a relatively simple internal domain. So let's take a look at this pipe first. You can see we just have one face that defines the cavity, and so it should be pretty simple to extract this using the fill operation. So if I go to the Tools menu and select Fill, I don't have to change anything. My extraction type is going to be bicavity. I just go ahead and select that internal face, press Apply, and generate. And now you can see very, very simply, if I hide the pipe body, I get exactly what the flow domain looks like on the inside, a very easy process. Again, this is a very obviously simple internal flow geometry or internal void geometry, but it captures exactly what I need. Now, instead, if I look at the actual ball valve part, and I look at the inside, well, now I have quite a much more complex internal geometry. Maybe one of the first things I want to do is get rid of this lower fillet here. So if I select this one face here and I go to Flood the Blends, I want to just capture that lower fillet there. So I'm going to unselect a few faces here, and I want to try to get rid of that. So I'm going to try to use a face delete to minimize the detail there, at least in some way. So I select these faces, I go to the Create menu, and I select Face Delete. And if I go ahead and generate that, you see it gets rid of those fillets. So it basically tries to take the surrounding geometry and use that to remove the extra detail that I don't want for this purpose. Now, once I am done doing my defeaturing, we'll go back and try to extract the flow domain from this section. If I use the fill operation and I use the bicavity method, it's going to be very tough for me to pick all these faces on the inside. So I have two options. If I have a relatively simple external geometry, so the outside of my ball valve, what I can do is just go ahead and select all of the faces and then unselect the faces on the outside. Now, unfortunately for this part, I have still a rather complicated outside as well. You see I have a number of these faces here that I'd have to go ahead and unselect. So that's not really a practical solution. So instead, what I'm going to do is use the by caps method. And what that's going to require is that I create a capping body on this opening here and this opening here, right? That defines the openings to my internal void. So if I select the two edges that define the openings, I come up here to the concept menu. I can very easily create surfaces from those edges, right? That's one of my options here. So if I select that, insert into the outline tree, and generate it, what you can see is I get two surface bodies, and you see in the outline tree just the same, that are going to cap off the ends of my ball valve structure. So very simple, very easy to do. If I come to my fill operation now, I want to change the extraction type to by caps. And I'm going to target just the selected bodies, just the ones I have selected right here. Now the next field is preserve capping bodies. That basically dictates whether I'm going to keep those surface bodies I created. Generally speaking, you're not going to need those, so I'm going to leave that as no. But maybe I do want to preserve the solids, which represent the ball valve itself. So I'll go ahead and generate that. And if I hide everything except for the geometry, what you can see is I get the complicated internal structure gets extracted in a very easy manner. So I have exactly what I'm looking for in just a few short clicks. I mean, that took me all of 2 minutes maybe to do, and I'm sure if I wasn't on the phone, I'd be able to do it a little bit quicker. Okay, so now that we've talked about internal flow domains, let's do our next poll here. So I'll open that up. And we're going to get a little feedback here on which tool you're using currently to do your flow domain extraction. So let me open that poll up, and we'll take a minute and get your feedback. Okay, looks like everybody's submitted their answers there. Let me close this and save it. And it looks like we have a few people using ANSYS DesignModeler, but some people also still using their CAD program. So hopefully we can show you the utility of ANSYS DesignModeler and why you'd want to be using that instead. Okay, so let's go back to our PowerPoint here. And the next topic we're going to discuss is external flow domains. So external flow domains, we have a little bit of a different concerns. Typically, our concern here, rather than cutting it at a specific location in a larger physical system, like a piping network, is that we want to make sure our domain is large enough so that the gradients at the boundary of our solution fields aren't too big. So if we have a solution or a problem like we have here where we have a wind turbine and we have air coming from the left to the right and flowing in one predominant direction, I'd like to use this useful rule of thumb where we have, I use the dimensions of the object that the air is flowing around and use that as the basis for the size of my flow domain. So I'd like to take the height and use at least, two times that in front of the of my object and a little bit more downstream, and then also ample space on either side and above the object. Now again, these are just rules of thumb, but usually a pretty good starting place for my flow domain. We can always go and run a first cut solution and come back and change them if necessary. Now inside of DesignModeler, we have an operation called the enclosure operation that's ideally suited for doing just this. Now, if we were to do this in a CAD program or without the enclosure operation, what we need to do is first create a sketch of the shape of our flow domain, then extrude that so that we have the three-dimensional volume, and then do a Boolean subtract so that we subtract out the CAD part or our solid body from the flow domain. The nice part about the enclosure operation is it does all of those things for you. So all three operations in one. We can create a flow domain of several different shapes And we also have very detailed control over the size of the enclosure, so we can specify how much basically slack from the CAD part we want on each side of the part, and how much space we want between our part and the boundaries. So a very useful feature. And I also like to point out that it's useful for internal flow domains as well. Sometimes if you have a complicated internal flow domain where you have multiple parts coming together to form the boundary of the internal flow domain, if those parts don't fit exactly together, it can be difficult to form the internal flow domain. So I oftentimes will use the enclosure operation in order to determine where I have leaks in my solid bodies, so where those bodies aren't coming together and touching each other exactly as they should be. Just another quick note on the use of the enclosure operation. Okay, so let's come back and do our last poll, and once we come back from the poll, we will do our final exercise or final demonstration of the enclosure operation, and we'll wrap things up for this e-learning session. So we'll open this up and just get an idea of where you guys are facing your biggest challenges in preparing geometry for CFD. And that should do it. So it looks like we're pretty much split between CAD cleanup and geometry simplification, with a few people saying domain extraction is cumbersome as well. So hopefully the tools that we've showed you today will help you, and you'll be able to explore with using those more successfully. Okay, so let's take a look at extracting an external flow domain. So come back to Workbench. I'll insert a new DesignModeler component system, and we'll open that up. And I'm going to go ahead and import a parasol file of a fuselage wing, a fuselage and wing section. So let's generate that. So if we take a look at this, looks pretty clean as far as the geometry definition. But maybe I want to try to clean up some of these faces first. So before I go ahead and extract my flow domain, I'm going to do a little geometry simplification. And in this case, I'm going to use the merge operation. So from the Tools menu, I'm going to select Merge. I'm going to change my merge type from edges to faces. And I'm going to use the automatic search tool. So I want DesignModeler to go out and search for clusters that it thinks are suitable for merging. So if I go ahead and change Find Clusters Now from No to Yes, I can see that it selects 17 different clusters as potentially being merged. And if I take a look, maybe they're on the inside here and on the top of the wing, where I have 4 faces that maybe I can merge into one. So let me go ahead and generate that. And hopefully when it's finished generating, as it goes through each cluster and tries to merge, it will come back successfully and have them merge together. And we'll have a much simpler definition of our geometry and make our lives, when we get to the mesher, a lot easier. And so it did. So what we have now, if we look, for instance, at the top of the wing section, oops, zoomed in a little too close there. What you see, we zoom in on the top of the wing section, and consolidated those 4 surfaces into one, made a much cleaner definition. Additionally, on the inside of our engine here, so it looks a lot nicer. Again, this is a nice automated tool for cleaning up your geometry. So once I do a sufficient level of cleaning it up, I come back to the Tools menu and I select Enclosure. And the first thing I have to select for the enclosure is what shape I want it to be. Now I have the option of using a user-defined shape or a sphere or a cylinder, but in this case what I want to use is a box. So I'm going to use just a rectangular shape and use that to define my, my flow domain. Now what we want to specify, or what the enclosure operation requires, is that we specify the cushion on each side. So in each direction, we want to know how much space we want between the fuselage and wing section and the boundary of our enclosure. Now we can do that in 2 ways. We can say, I just want a uniform set cushion in all directions, and it will go ahead and enforce that. But for a case like this, a non-uniform cushion is usually a little more useful. So in the X direction, I probably want a larger cushion in the downstream or in the wake region than I do in the upstream. So if I look at the negative X direction, I can set that to be, let's say, 30 meters. But in the positive X, or downstream, I want to set that to a larger value, so I'll set it to 120, for instance, just to start with. And we can always come back and change these. Now, from in the Y direction on either side of the wing, I want to do, let's say, maybe 30 meters on either side. And we'll do, just for starters, we'll do 30 meters in the plus or minus Z direction. So once I specify these constraints, I go ahead and generate. And I'll turn frozen body transparency back on and hide the plane. So you can see I very simply and very quickly was able to specify the extents of the flow domain. DesignModeler performed the Boolean operation for me, made it very simple, and gave me ample spacing on either side of my fuselage and wing section. So a very nice, simple, straightforward operation, and that's really all there is to it. So at this point, we've kind of covered, how we do this in ANSYS DesignModeler. Hopefully, we've showed you a couple of things that you could go back and use on your own. A few points to remember. ANSYS DesignModeler allows you to do these geometry simplification tools on any CAD part that you import without affecting the original CAD file. It also allows you to easily and in a streamlined fashion extract any type of flow domain that you're looking to extract, whether that's an internal flow domain for which we're going to use the fill operation, or an external flow domain for which we're going to use the enclosure operation. So hopefully we've showed you a couple of things here, and thank you for taking your time to attend today's e-learning session. And if you have any questions, you can always follow up with us. We should be posting this WebEx to our website, so certainly check back for that in the future.